Hey folks, in this video we're talking about standard enthalpy of reaction, and so I would like you, dear viewer, to be able to define standard enthalpy of reaction, delta H reaction. This little knot there for standard. Cool. I'd like you to be able to define standard state and perform calculations using standard enthalpy of reaction. Let's get going. So standard enthalpy of reaction, that's the change in enthalpy of a reaction when chemicals are in their standard state. So assuming we're at standard state of 1 atmosphere and 25 Celsius, that's the heat exchange that's going to go on when a reaction occurs. So it's going to be heat or energy gained or released during a chemical reaction. And so yeah, the standard state is a phase of a chemical is found in 25 degrees Celsius and 1 atmosphere. So kind of like room temperature conditions. And the units we're going to use for this standard enthalpy of reaction are kilojoules per mole typically. So if a mole of substance reacts, according to whatever reaction, it should release that many kilojoules. Neat. But one thing that we have to make sure that we do is consider coefficients in the equation that we're using when we use these delta H's for calculations. Let's take a look at this. Here is an example problem. We got 2 moles of solid zinc that reacts with 2 moles of hydrochloric acid. 4 moles of hydrochloric acid according to the following reaction equation. So this makes sense. 2 moles of zinc needs to react with twice as much HCl, so 2 to 4 as a ratio. That seems good. That's within this ratio here. How much heat is going to be released by the reaction if our delta H is a negative 80.7 kilojoules per mole? Negative 80.7. If we have a negative delta H, that tells us we have, what is it, exothermic or endothermic? Think about it. Yeah, that's right. It's going to be exothermic. A negative delta H is going to be exothermic. Cool. So let's do this calculation. We'll take our 2 moles of zinc, and we can use this guy as a conversion factor because it's got 2 units in it. It says we got this many kilojoules for every 1 mole. So, bam, we can multiply that out, and we'll get this answer. But what if we did the calculation with our moles of hydrochloric acid? And we said, all right, we'll have 4 moles of hydrochloric acid. I multiply that by my enthalpy of reaction, and now I get a different answer. It's a bigger number. So which one of these numbers is correct? Pause the video and think about that for a second. Well, the correct answer is, which is it? It's this guy. And so the reason that this number is correct is because we don't have a coefficient here, so we don't really have to do anything to this moles of zinc before we start using it to multiplying it by our enthalpy of reaction. But for the HCl, because there's a coefficient on HCl in this equation, we have to take that into account. So the correct way to do this is we're going to first take our moles of HCl, and we're going to divide that by 1/2. Because for every 2 moles of HCl we have, that's 2 equivalents of HCl required to make this reaction go down. So that 2 there, that's where I got this 1/2 here. That's where I divided this by 2, because you need twice as much HCl to make this reaction occur. And so once I do that, then I come up with the same answer. Well, let's look at another problem, and why don't you pause the video based on what we just learned and give this a shoot yourself. Cool. Well, you pause the video and tried that out. We're taking, all right, 4.72 moles of iron reacts according to this equation, and we want to know how much heat is absorbed or released if our delta H is a negative 826. That's a lot bigger. Well, if it's negative, we know we're going to be releasing heat because a negative delta H is exothermic and it releases heat. But we also have to take into account this 4 that goes along with our iron in our balanced equation. So when we do our maths, we're going to have to, before we can multiply our moles of iron by the enthalpy of reaction, we have to divide that by 4 because our coefficient is 4 here. We need 4 what we call equivalents of iron to make this go down. So yeah, that's 4 tells me I'm going to have to divide my moles of iron by 4. Sweet. Well, why don't you, using the same equation, pause the video and give this one a shot. Okay, similar situation. Now we're talking about the oxygen instead of the iron, and we have 95 grams. Well, we can't make grams interact directly with this. This is kilojoules per mole. So if we want to take our 95 grams and do some chemistry with that, we're going to have to convert it into moles first. We need moles if we're going to multiply with this guy in a meaningful way. So we'll take our 95 grams of oxygen, do some sweet X-line action with that molar mass, and we can convert this. Oh wow, I got fancy. And so now this will give me the moles, and then I can divide by 3 and then multiply by my enthalpy of reaction. And so this is all my steps put together and gives me a nice fancy answer of, wow, negative 817 kilojoules. That's how much energy was released. Well, Stuff like that is what we're going to use the enthalpy of reaction for. We also might calculate the standard enthalpy of reaction using data. So you might say, oh, this many kilojoules are released when this many moles are reacted. With that, you can figure out the standard enthalpy of reaction, which we've alluded to in a previous video. Anywho, that's the end of this one. Pretty short. Ta-ta. Have a great rest of your life.